Okay, good morning, students. Today is June 7th, Tuesday. Today we have, we're going to say a couple of words about the result of the assignment 1, which has very strange results, to say the least. Then Engineer Isaac is going to explain what are we going to do in our lab. And we have for today also to do the design of the experiment. We have to think about that, okay? We are going to go work in groups, okay? Then we're gonna have a break, and when we return, I would like you to take a quick look to have a general idea how quiz 1 looks like, okay? So I brought the quiz from last year, and we're going to solve it by groups again. And at the end, hopefully we will have about 15 minutes to talk about the solutions, answer any questions for these weeks, these days, and that's it, okay? More or less, that's the idea. Okay, so I'm going to, I can find it. See if I can find it. Here it is. Okay, let's continue. Okay. Andy, confirm me that you're looking to my projection. Andy, confirm me, please. Anybody?
Yes, doctor.
Okay, so I'm going to say two words
doctor.
about the result of the assignment number 1, okay? These are the scores, the results of the evaluation, okay? On the X, you have the number of the student, okay? And here you have the grade, the scores that you obtain. This is the average. The average is about 51. So as you can imagine, an average of 51 is not something which I like. See, I'm worried because usually when you have an assignment, you are supposed to come out in this area. Okay, so this, I don't know what they are doing. And even these people here, okay, they're just around 60. So if you have questions, if you don't understand something, you have to say, you have to come to office hours and things like that, okay? That's one thing. Here, this is the histogram of the scores, okay? So here, you're supposed to be, okay? So if you are here to the right, that means that you're above 60. And you see that all of these right now, they are behind the level for approval of this class. That means that you better start working. because this is a review. This first homework is the review. So you were supposed to have already this material, okay? Something else, this is the number of hours, okay? This is number of hours you reported, okay? And these people here, they say that the time is larger than 60 hours. That's a lot, okay? So in some other time, I would like to contact these students, because that it just looks too much, okay? Another thing is these people here, okay? This did not report hours employed. And these have a penalty of 5 points, okay, man, of 5 points. I insisted in the problem formulation, and the assignment sheet is specified that you have to report the hours per problem. So you are penalized if you are here. So in this homework, in this assignment, don't forget, you have to tell me how many hours did you spend for every problem, okay? The average is about 16 hours, okay? Which is correct, is adequate. That means that if you have 2 weeks for this, that means that you are using about 8 hours per week, and that's enough, okay? That's enough. So from here, 2 messages. First, if you do not understand something, you have to come to office hours. You have to send a message, either to Engineer Isaac, to Andy Miranda, or Maria Sayo, or myself, okay? We have office hours all over the week. You know our email addresses. Ask if 2 or 3 people mention that they do not understand one question. That means that I didn't explain correctly. But the only way I can realize that this is correct, something was not explained correctly, the only way I have is that you mention. That's the only way. Otherwise, I'm going to assume that it is well explained, and it is not. The problem is that I don't have a way to know that this assignment was not correctly explained, unless you start asking me about it. Okay, people? So let's go now to the description of what you are going to be doing Wednesday and Friday. Go on, Isaac.
Okay.
Please, everybody, this is the last session before the quiz, before the evaluation. Everybody turn on your cameras so we can know you. Go on, Isaac. I'm sorry.
Okay, good morning, students. I'm going to show or say a general description about the experiment that you're going to do in the lab, specifically Wednesday and Friday. In these 2 tests, you are asked to calculate the shear stresses and the effective breaks in these 2 cases. So the first case consists in an aluminum beam that is simply supported. You can see in the support in the left end and in the right end, and the first test consists in you apply force, but this force is divided by 2 because this force is contact by 2 supports. Okay. Immediately you see in the right hand side that the free body diagram. So you see the beam, aluminum beams that is simply support, and you see these two force that is applied in asymmetrical form. So the section that you have to analyze is in this part. So because in this part, I installed the string gauges. So for this first step in these configurations, so you have not shear force between this distance. So you can check in your house. Okay. So this is the first experiment. So you have to apply force once, 2, and 3 times. So and then register the strain data and force. Okay. The second step is similar. So this aluminum is simply support, but the force is like a concentrated force. So the distribution of the shear force is different between the last one. Okay, so in this case, in these sections, you have shear force. Okay, so the data of the string gauge is different. Okay, the profile of the beam is the cross sections type I cross sections. So you can take the dimension when you come out in this lab. Okay. The description of the equipment is the following. So you see that in the flange on the beam, there are 4 string gauges that is to calculate the effective breadth, and then in the web around the neutral axis, so you see there are three string gauges. So this data for these string gauges is to calculate the shear stress using more cycles. Okay, you have to check this information from past course. Okay, and in order to register strain data, so you have to connect these string gauges to the acquisition strain equipment like this, and then in the same form connected this strain equipment to the computer. And in this computer, you see in the desktop on the computer that there is a program called National Instruments plus Omega. So in this experiment, you are going to save strain data and force data simultaneously. So this is a setting for acquisition strain data. In the other case, also, you have to register force. So, but how you apply force? So, in the Simmer lab, you see a hydraulic system. So, but how works this system? So you see that there is a little tank oil, okay, hydraulic pump, and then you see two hose pipe, and finally the piston. Okay, if you want to move the piston downward, so the pump push the oil for this line, this pipe, and then the piston go down. In the other way, if you want to go up the piston, the pump push the oil for this line, and then the piston go up. Okay, so this you see in this part the the pressure sensor in order to see the maximum pressure that you apply in this moment. In this moment, this pressure sensor is configured that the maximum force is 4 tons. But remember that the load cells, the capacity of the load cell is 2 tons. So you have to be careful when you apply force that not exceed this force. Okay, you have to be careful. And then if you want to control or change the velocity of the movement of the piston, you have to use this valve in order to change the velocity when you move the piston in the down direction. Okay, pointing downward. Okay, the connections, the piston is connected to the load cell, and this load cell its capacity is 2 tons, and this load cell is connected by a cable, and this cable you have to connect it to amplify is in order to see a better signal. Okay, this amplifier needs a power supply of 12 volts, and then for this amplifier you have to connect to the Omega acquisition card. And also, this acquisition card you have to connect to the LabVIEW program. So remember that in the desktop of the computer, there is a program called National Instrument plus Omega, because we want to register string data and force data simultaneously. Okay. Again, when you click on this program, you have to see two interfaces: one for a user, and the other interface for programming. For this interface, you see these two options, these two graphs. So this is to setting the Omega acquisition card. You have to select the channel that in this moment you are using. This is very important, the scan rate. So remember that the minimum value is 1000. So the total scan is 100 but this value is per loops. Okay, so this is the minimum value. That is, these two values is by default. So 1000 scan rate and 100 to the scan per loops. Okay, these two configurations will be the same of the setting of the national instrument cards, will be the same. Okay, and when you run the program, you see the signal in these two graphs. In this graph, you see the force in millivolts, and then in this graph, you see the the signal in the strain. Okay, that is a dimension. In order to
Question, Isaac.
yeah.
Here, we should have somewhere clearly the value of the signal for the force, which is the maximum value that we can accept in order to avoid any damage on the equipment.
Okay. The
We should
the
calculate
conversion. Okay, the conversion of the in order to obtain the maximum force is 10 volts is equal to 2 tons. So this is the conversion. Student, please. 10 volts is equal to the 2 tons. In order to that, when you apply force, you have to see the value of the load force in millivolt and convert quickly in order to don't stick this force.
Yeah, but in general, I would say that we shouldn't go beyond, say, 400 kilograms. So please calculate how many volts is the maximum that you are going to have in order to avoid not exceeding 400 kilograms. Anybody? Anybody? Go on, Isaac.
Okay. Any student, can you calculate this problem, the maximum force, the maximum millivolt that you expect when you apply force?
2 volts.
That is 12 to 2000 millivolts, right? Santos?
Yeah.
Yes.
Okay. So you have to be careful that this signal not exceed, not overpass the 2000 millivolts. Okay.
If you can be, say, about 1,000, 1,500, that's okay.
Okay.
So from that point and below.
I have a question.
Yeah, go on.
This change in the voltage respect kilograms is linear or no? Or no?
Yeah, yes. This conversion is linear.
If we had the time, okay, in a regular session, we would ask you to prepare a
Calibration
graph, exact, a calibration table. But unfortunately, we have no time for that. So you would take the load cell applied forces that you know and measure the voltage that it's the output. And then you plot the force versus the voltage, and you will get the conversion. Unfortunately, we have no time. Isaac did it, and that's the number that he is telling you. It's 0.2, 0.2.
Okay. So finally, in order to see that, you have to program this in this library program in order to read the data from acquisition cards and then show in the plot and save in txt file. So this is the program in order to read from Omega cards, and this is the program for in order to read from National Instrument cards. Okay, but in general, these two programs is consist to read the data from the acquisition cards, and then show the signal in this plot, these two graphs, and then save save the data in a TXT file. Okay, but this program I have created, so you have to just use this program. So in order to use these programs, so just to you have to use this interface for user. So you have to set in the channel of the Omega acquisition card, and then specify the scan rate. No more. Okay, if you have questions, let me know now.
Excuse me,
Sí.
is that,
Yes.
do we have to write in a TXT program in the
Yes.
the presentation?
Tell me again.
Do we have to write a TXT program?
Yes. Yes. When you stop the programs, these live view programs automatically save in these two files with different name. With the Omega cards, you can set in the name. Maybe you can write the name of the result data. And by default, the national instrument cards give us a string with the number of the number of the file is a string, whatever, and you see. But yes, the program automatically give us two TXT files, one for the force and the other for the string data.
Zach, don't you have one of those files at hand so you can show them?
Okay.
After you finish this.
Yeah, this is the finish. This is the end.
Yeah, okay. Please show them. It's a good idea.
You see, for example, Omega data for the force, and then a strain gauge for the strain gauge. So in this folder, you see these two files. You see, Santos?
Can you open?
Okay.
Can you open one of those files?
Yeah. Yes. For example, the strain gauges.
There's nothing. Oh, there you go.
This is the other experiment, but this is similar when you obtain the value of the strain. Okay, this is the column of the times, and then the value of the strain gauge. In your case, you have 7 strain, so you have 7 column in this part. Okay, in the other TXT files, Omega, so you see 2 columns, one for the times and the others for the force in millivolts. Okay, but you have to convert this millivolt to a kilograms. Okay, that's all, doctor.
So you are going to receive, after you complete the test, you stop recording information. You are going to have 2 files. Test. So
Yes.
you are going to have a total of 6 files. Okay, 3 for the first test and 3 for the second. Okay, and the information from each one of the 3 is supposed to be the same. But you know that this is experiment, so there are many things that can change. Yeah, there will be some differences. Okay, so what you have to do is identify each one of the columns, okay, to try to see at what position on the beam corresponds each one of the signals, and then you have to plot against the force, because that's what we need. And the problem is that the force is in the other file. So you have to take that information, put it in the same file, bring it from Excel, import it from Excel, and with the column of millivolts, you convert that into newtons. And then you have to do the calculations, okay? With the 3 signals around the neutral axis, okay? With the 3 signals in X, in Y, and at 45, you can calculate gamma. I can comment that later. From the signals on the top, I will explain after we return from next week. I will explain how to calculate what we call the effective breadth with those signals. So you have to do those 2 calculations. Okay? That's the general idea of what we need to do. Okay. Let me draw here. Can I draw here?
Okay.
Yeah, exactly. I don't know. Oh, no, I can. Let me give me here. I have, even if you believe it or not, here I have 3 strain gauges. Okay. When you come to the lab, you will see it in detail. There's going to be one in this direction, in the X direction, that measure the epsilon in the X direction. More or less, what do you think will be the value from that strain gauge? Mr. Janos, the value from this strain gauge, how much is going to be that value in the X direction on the neutral axis?
What is strain gauge?
How much is going to be epsilon X? Mr. Janos.
What is strain gauge, doctor?
This one here, number 3, it's located in the X direction.
Number 3.
How much is the stress, the normal stress on the neutral axis? Mr. Hidrobo.
0.
0, doctor.
Yes. Yes. So the value on that signal is going to be very small. There is another one in the vertical direction. This is the strain gauge number 1. This is located in the vertical direction. And there's going to be another at 45. So here you have six cables, 2 for each one of them. And each one of these pairs take the signal to the data acquisition card, and you register how much varies the strain in X, in Y, and at 45. Once you have that, okay, once you have that, then you can prepare, remember in solid mechanics, you have to prepare the Moore circle, but for the strain. You can review that in Popov's book. So here you're going to have epsilon X, and in the vertical you're going to have gamma XY. So you have a value here, a value here, and a value here. Be careful with the signals. Remember, when you go in one direction and in the other, there's a change in sign when you compare the real world with the Moore circle. Okay, After you calculate gamma xy, how can you calculate the shear stress? Mr. Guaman, how do you calculate the shear stress from gamma xy? Mr. Guaman, I cannot hear you. We have a problem. Mr. Romero, how can you calculate shear stress from gamma xy? Mr. Romero, Jandri Romero.
Is necessary to obtain the shear force.
No.
Multiply.
Come on. What is gamma xy? What is gamma xy? Isaga, what is gamma xy? What is this? Gamma xy. Mr. Isaga or Isaga, Yanni Isaga?
Present.
What?
I'm here. I'm here. Is the is part of
Gamma, gamma xy. What is it, gamma xy?
It's a deformation of
Exactly. It's the shear
deformation.
Shear strain. Okay. From the shear strain, how you calculate the shear stress? Miss Sanchez, how do you calculate the tau xy from gamma xy? Miss Sanchez, are you there?
Yes, I'm here. The tau with the shear stress.
No, the shear stress is what you want to calculate. Mr. Chin Chin. From gamma xy, how do you calculate tau xy? Mr. Chin Chin, are you there?
Yes, doctor, I am here.
So, Mr. Ramirez, come on. You copy in solid mechanics. That's Hooke's law. Anybody? How do you calculate tau xy from gamma xy? Anybody?
Shear stress multiplied by shear stress multiplied by modulus.
That is strain.
Yes, shear strain multiplied by shear modulus.
What's the letter that we use for shear modulus?
G.
G. Carol G. Do you remember that? Carol G. Yes. You multiply G times gamma xy and you get tau xy. That's experimentally. And then you compare that with the theoretical value, which is V Q over I sub C and B, little b. Did anybody want to go to the Karol G concert this past weekend? I did. Okay, so that's for the information about the neutral axis. Okay, you take these three gamma, three epsilons in X, in Y, and at 45. And then, see here, you see that these are the flanges. If you have on the flange, okay, and you apply beam theory, what's going to be the relationship between the values of epsilon here, 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 and here? They have to be the same. What's the formula to calculate the stress in the case of beam bending? How do you calculate the normal stress in case of beam bending? Mr. Zurita, what's the formula? How do you calculate the normal stress in beam bending? Mr. Zurita.
Good morning, doctor. Normal stress multiplicate no.
The strain multiplied by
Miss Jimenez, Miss Jimenez. People, you can tell me anything, but you cannot doubt. These are basic formulations. Miss Jimenez, how do you calculate normal stress in beam bending? Miss Jimenez, you're not here. Please, those who do not answer.
Is the moment by G over inertia.
Exactly. Minus bending moment times Y divided by inertia.
Okay.
So if these are located on the top, what's going to be the relationship between the values of epsilon on the flange? They should be the same because they are in the same vertical position from the neutral axis, right? But you will see that there is some difference. Why? That's the reason of the next subchapter, okay? When you have shear force, there's going to be some influence, okay? And the influence will be analyzed, estimated using the concept of effective breath. Okay, so here there's going to be some variation, and you will have to plot it, something like this. Okay, and with this variation, you will be able to calculate the effective breath. Okay, with effective breath, you can calculate. You can compare it with some formulations from the DNV Society of classification. Okay, so from these values of epsilon on the neutral axis, you calculate gamma xy, and from there you calculate tau xy and compare that with theory. With the values on the top, okay, you calculate the effective breath and you compare the effective breath with the value that you obtain applying the formulation from DNV. Sorry to interrupt you, Isaac. Let's go on. What do we have to do now, Isaac? Go on. Isaac.
Okay, and now we're going to work in groups in order to prepare the design of the experiment. So Andy Miranda, Daniela Sayo. Can you?
Exactly. Send everybody to their groups. We're going to do this. They are 12, right? So Isaac, you work with groups 1, 2, 3. Andy, you work with groups 4, 5, 6. Maria Daniela works with the next 3, and I work with the last 3. Okay? So 3, 6, 9, 12. Okay, go on. I don't know who is going to form the breakout rooms. Yeah, for this exercise, only 5 minutes, people. 5 minutes only.
Okay.
Okay, send them.
Engineer, is necessary speaking English or no?
No hay problema. Lo podemos hacer en español esta parte. Verás, los grupos, de su grupo solamente están ustedes dos.
Sí, doctor, sí, ingeniero, es que creo que están yendo a la U porque tenían
Lección de estabilidad. Ok. Entonces, bueno, lo que Lo que tenemos que hacer es el diseño de experimentos. Entonces, abran por favor en el aula virtual se les envió la parte de... Preparen las cámaras, Raúl y Soli. En el aula virtual se les envió la práctica y hay una parte de diseño de experimentos que vamos a hacer ahorita. En 5 minutos. Digo, prendan la cámara, no la apaguen. No la apaguen.
Allá, pero ¿está en qué parte? ¿En módulos? ¿O es
En tareas, en tareas, en tareas. Pueden descargarlo y yo también tengo por aquí.
donde dice laboratorio de experimento 1?
Ajá. Pues Miranda, ¿tú te tocaba aquí? ¿O cuál me tocaba a mí?
4, 5 y 6.
Ah, entonces mira el 1, 2 y 3.
Claro.
Entonces, ¿por qué me enviaste al 4? Habla bien. Ya, ya.
Es que antes de crear, antes de que nos dijera ya estaban creados los grupos.
Ya, bueno, ya me salgo entonces. Ya.
Ya,
Se
listo.
quedan con Miranda, ya. Voy a decir, ya, esta es la primera. Tengo que ponerme. No entro, pues.
Voy a ver si lo puedo sacar de aquí.
Aguante.
No puedo.
Que las reacciones.
Yo tengo una pizarra aquí. Déjame compartir la pizarra. Para que si alguien tiene que poner aquí. Y...
El líder.
Bien preparada.
Ahí está. Ya.
Ya, tenemos que encontrar solo las condiciones de frontera, ¿verdad? Nada más.
Claro. Sería indeterminado, ¿no?
Determinado.
Sí hay dos reacciones.
Determinado.
Determinado, sí hay dos reacciones.
No puedo escribir en tu cosa.
¿Cuántos minutos tenemos? ¿Cuánto tiempo tenemos?
5 minutos, 5 minutos.
Ah, ya pues aquí salen las reacciones que es igual a F medios y F medios en el test 1. Y en la segunda, igual. F medios y F medios, ¿no verdad, Isaac?
¿En cuál?
Y las condiciones. Tenemos que encontrar las condiciones de borde, las condiciones de frontera.
O sea, lo que tienen que hacer es, bueno, pensar pues cómo es el diseño de experimentos, ¿no? ¿Cuál es el procedimiento que deben seguir para alcanzar los objetivos específicos? Entonces, deben comparar la parte teórica con la parte experimental. Entonces, de forma teórica, deben sacar el shear force en ambas condiciones, ¿verdad? Ustedes ya saben, entonces primero deben, para ambas situaciones,
Sacar
en la sección de análisis, ustedes aquí, si ustedes hacen desde la fórmula normal, ¿no? ¿Cómo que se llama? Y XX igual al P de X, entonces si ustedes integran todo eso, les va a salir que aquí no hay fuerza cortante. Lo pueden hacer manual, pero directamente aquí no hay fuerza cortante. Ya, entonces aquí es 0. Entonces, por lo tanto, la fuerza cortante es 0. Entonces significa que los valores que deben encontrar, o sea, ustedes tienen 7 strain gauge, ¿verdad? 4 en el ala y 3 en el alma. Los 4 que están pegados en el ala de la viga es para calcular eso luego lo van a hacer, o sea, parece que no nos va a topar en este experimento, solamente van a registrar los valores y luego van a hacer esto, o sea, a entenderlo un poco más, porque no lo he explicado muy bien el doctor. Nos vamos a concentrar en los string gauges que están ubicados en el ALMA, ¿no? En la parte, los que están ubicados de forma horizontal, vertical y inclinado, esos tres. Entonces, debemos de pensar cómo calcular, como explicó ahorita el doctor, pues, ¿no? El círculo de Moore, ¿ya? Y obtener el esfuerzo cortante. ¿Sí? Y de forma de forma teórica, rapidito, ¿no? Aquí el B es 0. Entonces, ¿qué concluimos con el
El esfuerzo, no hay.
no hay?
No hay
Ok.
esfuerzo.
Y en el otro, aquí sí hay.
En el otro sí hay.
Entonces, básicamente este es sencillo. Aquí ustedes tendrían, si este es F medio, ustedes acá tendrían F medios y acá tendrían otro F medios. Entonces, básicamente sería, creo que es negativo así, sería así. Y luego así y luego así. Ya, entonces, bueno, si F medio sería la fuerza cortante, ¿no? Y con la fuerza cortante pueden calcular el tau, ¿no? El tau es aquí es igual a B por el Q,
Digo por
¿ya?
ahí.
Dividido para la inercia. ¿Y qué más? Se me escapa algo.
Por la.
Por B.
Por B. Por B. B.
¿Ya? Entonces, en el ala, ¿no? Ustedes tendrían esta sección de aquí. Perdón, que no sé, no tengo el pulso del doctor María.
No te preocupes.
Entonces, están ubicados estos tensómetros justo aquí. Entonces, en este caso debería haber máximo, o sea, el Q es máximo, creo que va, ¿cómo
En el
era?
tren,
¿Cómo
Medio.
era?
En el eje.
a la mitad.
Era así y luego algo así, ¿no?
En
O
la
algo
web.
por el estilo. Entonces, me imagino que debe ser máximo. Ya. Entonces, avancen por favor con eso.
Ya.
Eso. Y de forma experimental, pues como el círculo de Moore, ¿no? Habría que revisar eso en mecánica de sólidos. El esfuerzo. El esfuerzo.
Y la parte experimental, me preguntaba si...
O sea, tú tienes, a ver, tienes la deformación así horizontal,
Ajá.
así inclinada, y el otro creo que vertical. Entonces, de
Ya.
estos habría que calcular, como dijo el doctor ahorita, con un método, o sea, si el uno está horizontal, el otro vertical y el otro 45, cómo obtener el tau.
A partir del círculo de Moore.
Ajá.
Pero el doctor dijo que a la derecha dibujábamos el strain y vertical el círculo de Moore. Entonces, si son 3 strains, son 3 puntos.
Sí, son 3 puntos. O sea, mira, hay que ver la fórmula. Tú en la fórmula necesitas 3 valores para poder hallar este gamma. ¿No? Con el gamma ya puedes calcular el esfuerzo cortante, que es gamma por G. Algo así, ¿verdad?
Sí.
Entonces, pero hay que revisar el círculo de Moore. Y yo ahorita no recuerdo, tienen que revisar eso. Bueno, más o menos, me voy al siguiente grupo.
Ya, gracias.
Gracias, ingeniero.
Hola, Inge, ¿cómo está?
¿Cómo está? Ya, listo. Entonces, ya, primer caso, bueno, ya las condiciones de frontera, bueno, y toda la
Sí,
cosa.
ahí nos faltaría sacar solamente las ecuaciones de cuando L es igual a donde está cada fuerza aplicada en el domain de la viga. Y ahí sacaríamos cuatro ecuaciones más para sacar AY y BY, porque nos faltan ecuaciones ahí. Entonces tomaríamos con esas distancias donde están aplicadas las fuerzas. Y abajo, en cambio, en la mitad de la viga está aplicada F y ahí tendríamos la condición de que
Espérate.
del cortante y el momento.
Aguanta, espérate. Ustedes tienen que el X y el desplazamiento de 0, ¿ya? Y el otro es BX.
¿Cómo? Ah, no, ese es el cortante y el slope, sino que no puedes escribir bien con él. O sea,
A
simplemente
ver,
analizamos
a
las
ver,
condiciones de
a ver, a
frontera.
ver, a ver. Las condiciones de frontera son simplemente soportadas. ¿Cuáles son las características de simplemente soportadas?
La deflexión 0 y el slope 0.
No, señorita. Simplemente soportada. Desplazamiento 0 y momento 0. Empotrado es desplazamiento 0 y pendiente
Sí.
0.
Sí, perdón. Me confundí.
¿Ya?
Entonces, hay que cambiar en ambas.
Sí, señor. Entonces, ustedes deben calcular para ambas situaciones la distribución de esfuerzo cortante. Si ustedes sacan, porque este es un caso primero, determinado o indeterminado. Es determinado porque solamente tienen dos reacciones. Determinado. Entonces, lo pueden calcular rápido. Entonces, en este caso de acá,
Sí,
pues,
me confundí, ingeniero. Yo escribí eso,
ya,
sino que me confundí.
ya, en este caso, eh, ¿qué le iba a decir? En este caso, aquí no van a tener distribución, no van a tener dentro de estas dos fuerzas, no van a tener fuerza cortante y por tanto el esfuerzo también sería nulo. En cambio, en el otro, ustedes tendrían rápidamente, ustedes tienen fuerza aquí. Aquí no tendrían, ¿cómo sería la distribución de fuerza cortante?
¿En dónde?
En este de aquí, supongamos que este es A y esto de acá es, no sé,
Empezaría linealmente como, perdón, no sé si,
¿Cuándo?
voy a borrar un pedacito para rayar.
sí, sí.
Perdón, dije que me confundí.
Entonces,
Pero me confundí escribiendo.
tendrían allí, espérense, no lo borro, allí,
Desde
ya,
aquí
¿cómo sería?
arriba.
Ya,
Aquí tendríamos el primero, aquí hasta el punto A. Luego, supongo que bajaría hasta el extremo negativo.
o sea, aquí en este tramo es 0, esto
Hasta
es
ver,
0,
ajá. Sí,
ya,
aquí iría así.
y luego el otro lado,
Tendríamos, uy, perdón. Teníamos L. L.
Bueno, más o menos. Creo que es así, más o menos. ¿Ya? Entonces, creería si es que no es así o si es... A ver, déjame ver, este es el medio. ¿Cuánto valdría allí?
¿Cómo?
¿Cuánto valdría allí? O BY.
Ayer.
F medios. ¿Dónde? Acá, en el inicio.
Ya sacaron, si es que vale F medios. Efectivamente.
No hemos sacado, solo estábamos analizando las conditions.
Rapidito. Bueno, ese sería rapidito, ¿no? Bueno, ustedes sigan, puede ser que esa sea la distribución. Y la de abajo, la distribución, ¿cómo sería? Sería por aquí, luego me iría acá arriba, y luego sería así, ¿no? O sea, yo tengo aquí, sería acá, sería F medios. Esto de aquí sería, esto de aquí sí es fácil. Aquí sí sería F medios. Y acá también sería F medios. ¿Sí? Entonces, acá, aquí en esta situación, no hay fuerza cortante. Aquí sí. Entonces, a partir de allí deberían calcular el tau, que es la inercia para ver. Ahí está, B es Q, esta fórmula, ¿no? Esa es la forma teórica. Y la forma experimental, bajo el círculo de Moore. Entonces, avancen en eso, miren las características, o sea, las variables, cuántas veces se lo va a repetir, creo que son 3 veces, el experimento, y sigue. Voy a continuar con el otro grupo, después me está llamando el otro. Aló, doctor. Ya. 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 Ok. 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 Ya, doctor. Ya, bueno, más o menos de forma teórica e experimental. De forma experimental, ustedes tienen 3 puntos de los... O sea, nos vamos a concentrar en los extensómetros que están en el ala. El uno horizontal, vertical, inclinado. Entonces, con esos 3 valores podemos calcular el gamma. O sea, nosotros tenemos deformación así y deformación inclinada. Entonces, con esos 3 podemos obtener gamma. Y con gamma podemos tener perdón. Si yo tengo con gamma multiplicado por y, eso sería tau. Entonces, podemos comparar la parte teórica con la parte experimental. Entonces, la revisión de cómo obtener gamma a través de estos 3 extensómetros es a través del círculo de Moore, pero usando deformaciones unilaterales. O sea, eso tienen que revisar la mecánica de sólido. Y revisar bien esto de acá, la parte teórica. Más o menos. Más o menos. Ya. Más o menos digo, porque voy a cambiar de grupo.
No, sí, sí.
Sí, sí.
Sí lo entendemos.
Ya.
No,
Ya. A ver. Ya.
mismo.
Ya,
Le está considerando acá como,
¿cómo han avanzado con el diseño de experimento? Rapidito, ¿alguien ha hecho? ¿Me muestra, por favor?
ingeniero, una pregunta. Buenos días. Aquí hay una pequeña duda en lo que dice el test 1, no shear, ¿a qué se refiere con no shear? Y acá en el test 2 con
Ya
con
hicieron,
shift,
ya
no sé.
hicieron la distribución de fuerza cortante. ¿Cuál
O sea,
sería
estamos,
la distribución de fuerza cortante en ambas situaciones? ¿Cómo sería? ¿Ya la realizaron?
pues estábamos chequeando cómo es lo de los objetivos y qué decía, pero en realidad si algo escrito todavía, alguna formulación, no.
Ustedes
Asumíamos que, por ejemplo,
tienen que comparar el shear estrés teórico con el experimental. Con el experimental, la forma experimental, ustedes nos vamos a concentrar en los 3 tensómetros que están en el ala y con esos 3 puntos de horizontal, vertical e inclinado vamos a obtener el gamma. Con el gamma y el módulo de corte tenemos estado experimental. Ahora, de forma teórica, ustedes tienen la viga, capítulo
condiciones de
1,
frontera.
condiciones de frontera, simplemente soportado, sacan la fuerza cortante y con la fuerza cortante tienen que el tau es la fuerza cortante por el Q dividido por la inercia por el espesor, ¿verdad? Entonces,
Sí.
pueden comparar ambas cosas. Entonces, eso. Por eso es que el señor ya nos dice, ¿por qué dice no shear? Porque si ustedes hacen la distribución de fuerza cortante, en ese espacio no hay fuerza cortante. No hay.
Por lo que
Pero
las
en un
fuerzas están
caso no hay.
aplicadas.
Ajá. Por eso le digo, pero ya, pues,
Ya.
simplemente soportado 2 fuerzas, hagan ustedes la distribución de fuerza cortante.
La boundary conditions y su Z, entonces,
Van a andar en condition, pongan un momento flector cero, pongan desplazamiento cero y avance. Y miren la
ok.
distribución de fuerza cortante y se van a dar cuenta que en ese tramo no hay. En cambio, en el otro sí hay. En el otro no, en el otro sí. Entonces hay que ir haciendo, ¿no? Bueno, vamos, creo que ya, eso es lo más o menos de forma resumida, vamos a la sesión general. La sesión, a ver.
Y por ejemplo, la parte que nos dice lo teórico, ¿no? Que igual que decía esto de las fórmulas del DNB, cosas así en el objetivo específico.
También, pues hay que ver qué dice la regla de clasificación, ¿no? En esa situación.
Y por ejemplo,
Para el ancho efectivo sí hay una fórmula, ¿no? Y creo que lo otro no es de esa regla, solamente es para el ancho efectivo, pero el ancho efectivo, el doctor dijo ahorita que
la
vamos a
próxima,
esperar la próxima semana hasta que él explique esa parte. Solamente vamos a tener los datos de los extensómetros de la parte del top, lo vamos a tener allí, me imagino, hasta que él ya avance en esa parte y podamos usarlo.
y lo otro, por ejemplo, digamos, nosotros, me imagino que va a haber alguien al momento del experimento, pues también hay algunos de
Sí,
ustedes,
sí.
de los ayudantes. Digo, si la fuerza que se está aplicando va a aumentar gradualmente hasta llegar al máximo, por ejemplo, digamos, si vamos a aplicar máximo 1 tonelada, entonces se va aplicando con el pistón poco hasta
Poco
llegar
a
al
poco,
máximo, ¿no?
bien lento. Ajá.
Entonces van a haber como ciertas oscilaciones con respecto al tiempo y deberíamos coger al final la máxima.
No va a haber tanta
O,
oscilación, usted va a ver la curva que sube y luego al momento de descargar baja. No va a haber tanta oscilación. Pero
ya
sí,
listo. Y nosotros siempre en
ajá.
este caso, los valores de cómo es que se llama, ya ustedes los establecieron de cuánta fuerza se va a aplicar o por grupo nosotros tenemos que considerar cuánto.
Lo que pasa es que o sea, la celda de carga es 2 toneladas, no se puede pasar más allí. ¿Sí? Porque donde se pase 2 toneladas se quiebra, se daña. Entonces, estamos queriendo pasar, creo que el doctor dijo 400 kilogramos, porque tampoco habría que hacer algunos cálculos, bueno, rapidito, de ver cuánto aguanta esa viga de aluminio. Porque puede ser que pasemos de cierta carga. ¿Cuánto dijo el doctor? 400 kilogramos. ¿Cuánto dijo?
400 kilogramos.
400 kilogramos, ya, es suficiente, porque si pasamos de eso, puede ser que pasemos el límite de fluencia y el momento de soltar la carga quede totalmente deformada. Entonces, no queremos eso, solamente estamos en la parte lineal. Ya, listo.
Ya,
Cualquier pregunta, vamos
ya les.
ya, creo que ya. Okay. If any student have question about the design of the experiment, you have to tell me now.
Can you repeat the question?
Yes. What is your question?
No,
Or
no,
your
no,
doubt?
no. I didn't.
I don't listen.
Hello.
Yes. Go on.
We just enjoy the session right now, and you were talking about something, and we couldn't hear you.
Okay.
You were
We organize in group in order to prepare the design of the experiment, theoretical formulations, and the main characteristic of the experiment in order to prepare in a correct form for tomorrow. Okay, that this is the activity that we did.
okay.
Okay. So if any student have questions about design experiment, or you are very clearly in this that you have to do in this in the lab.
I have a question.
Tell me.
Can you repeat the relation between the millivolts and the force? I didn't.
The relation between
The millivolts and the
okay.
tones.
Okay. 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 10 volts. It's 2 tone. This is the formula. Okay. So in a summary, you have to prepare the distribution of the shear force in these two tests. When you prepare the distribution of the shear force, in the first steps, you have no shear force in this part. Okay, but in this part, in the test 2, you have in these sections, you have shear force. So the graph is that. So in this part, you have the reactions F divided by 2, and the other reaction F divided by 2. And this is the force. So the reaction is, in this part, is F over 2. But in this part, in this first test, there's no shear force. So in the theoretical forms, you have to calculate the shear force. So the shear force is, the shear stress is equal to the shear force. What else? Per Q divided by inertia per thickness, right? So you have to, this is the form that you have to calculate the shear stress in a theoretical form in these two cases. And in experimental forms, you have to, let me, with these three string gauges, you have to review the Moore cycle in order to obtain the gamma. when you take the gamma multiplied by multiplied by G, you get shear stress in a experimental form. You have to review the small cycle. So, and hopefully these two values is close, okay? Theoretical and experimental value. But you have to calculate the distribution of the shear force in these two cases, okay? For this value of the strain data, you have to save for this moment, and then when the doctor explain the concept of the effective ref, you have to calculate this. You have to use this data in the next week. Okay, but in this week you have to concentrate it in the shear stress. Students, questions?
What does mean that test number 1 has no shear?
Okay, because there are two tests. One, simple supported by the force is divided by 2, because there are the force is in contact by 2 supports in the top of the beam. Okay, in these configurations, when you resolve the problem and you obtain the distribution of the shear force, what is the distribution of the shear force in this problem? So you have to check, and in the middle, you don't have shear force, because test 1 is not shear. And
Please,
when you
okay, for the student who asked the question, please make sure that you are able to check what Isaac said. Isaac is telling you the stress force distribution on this beam has no shear force, zero shear force between the two, F/2 and F/2. Please sit and solve the problem and check that it's indeed free of shear forces. And in the other case, he explained to you the distribution is here, then have a jump, and you have another value. Check that. Check. Be sure that you are able to solve this. This is please, people, this is a statically determinate case. If you are not able to solve these problems, Isaac is in trouble, not me. Go on, Isaac.
Okay, this is easy to resolve. So, okay, so this is a determinate case, simple supports, displacement 0, moment equal to 0, the px, the p of x, these two force, concentrated force, so you can go on and obtain the shear force distribution in both exercise, and then go on. Obtain the shear stress in a theoretical form and then compare to the experimental form. Okay. So this is all for this experimental test. So now we are going to discuss in group the last quiz that this is taking in the previous years. So now we're going to work in groups. So the group number from number 1 to the 4th resolve the first problems. The number 5 group to the maybe to the 8 on the 9, resolve the second problems, and the 10 to the 12, the last one problem. Okay, I send you this this by Zoom right now. Okay, let me stop. Then by message and you.
Are you going to put it in a chat or?
No, I can't. By ahora
Let's take advantage that the Isaac is working. People, I have to be sure that the timing, the schedule, everybody understands, okay? So tomorrow, Wednesday, okay, we need to start at 8. And we are going to work with a group, 2 groups at the same time, okay? Because otherwise, we will have no time, okay? So 2 groups will be in the lab completing the experiment. They will do both tests, 2 tests, and they will have some results, and they will analyze that. At the same time, I will stay in the auditorium, and I will ask somebody randomly, okay, from the other 4 groups, okay? I will ask, get here, explain me something from either assignment 1 or 2. Very short, 2-3 minutes, that's all. Okay, when the 2 groups from the lab complete the tests, they will come to the auditorium. And the next two teams will go to the lab and on. Okay, that will be Wednesday and Thursday and Friday. On Thursday, 8 a.m., 8, you will have to be here. We will start the quiz. Closed book. It's about the material that we have completed so far. So it's related to assignments 1 and 2. 2-hour test. Any questions about this? About the timing? Questions about the timing? No questions.
It's
good.
I have a question, Doctor. It's mandatory that all of members of the group must be in the laboratory at that schedule.
Yes, because that's why we organize by groups.
Yeah, as group, we are specified that I would like to wear the practice for Friday because I can.
We ask you if you prefer one or the other day. And those groups who specify that they prefer to be on Wednesday or in Friday, Sayo and Miranda, they consider that and they put it at the day that you prefer. But you didn't say. That's why you understand, right?
I did.
I don't know. You have to talk to them.
Okay.
Because, I think there were 3 groups. They specifically said to us, I like to be on this day. I think Miss Aviles, she preferred to be on Friday, right? And she is on Friday, and with her group, of course. Yes. So that we tried. Go on. Is there any
Okay.
other question? Any other question? Any other question? No, go on, Isaac.
Okay, I send you the quiz one for the last years by Aula Virtual. So you have to turn out and work in groups. So Miranda, Andy, can you break down rooms?
Okay, good.
Okay.
We have only 15 minutes, people, for this because at 5 minutes before 9, Isaac, we have to get them back. Okay.
Okay.
And let's see if there is. Probably we will need some extra time, but we have to try to close by 9.
Okay. Vamos a hacer el ejercicio número 1. Entonces le tocó el ejercicio número 1. Ideas de cómo hacer.
Yo tengo una idea.
A ver, dice batch, estuve ya fresh work, no train, no way, facilito. Way distribution está en lista, ya. We consider concentrated loads, ya, and the end, dice, el valor requerido del Shear model. Ok. Entonces sería sigma, flexión de Bigger. Entonces sería sigma es igual a momento dividido para el módulo seccional, ¿no? Entonces debe sacar el momento de esa distribución, ¿verdad? Y, ok, ya. Tienen el casco, tienen la superestructura, tienen carga, ¿no? Y tienen, ya. Dice que
Pero
no tienen
consideramos
trimado.
que es como que la parte transversal es cerrado, es un cuadrado.
Claro, es una barcaza, pues dice box bars. Box bars.
Pero sin abertura o como una U.
Es como un barcaza
cajón.
cajón, pues cajón.
Ya.
Ahora, si dice que está en fresh water, o sea, tienen todas las cargas y tienen que colocar también la carga, la fuerza de bullantez, pues, ¿no?
Ingeniero, yo tengo
Bien.
como que, yo lo estaba como que haciendo. No sé si esté bien, para ver si puedo compartir.
A ver, comparta ahí rapidito.
Yo estaba practicando ayer.
Ya, para sacar esto, claro, la fuerza de bullantez debe calcular el peso total, ya.
En este caso yo tenía una duda. En este caso de lasters y de las maquinarias de 150 es considerado también como la fuerza concentrada. Porque no veo.
No dice.
No dice.
Ajá.
Pero allí, a ver, ¿cómo que no dice?
El ejercicio no dice. ¿Cuál es área superestructura más machine?
Pero dice que cargo es 22 y acá 22, 42, ¿verdad? Y es simétrico, pues. Si es simétrico sería 30, 60, menos 22, 30 menos 22, 8.
8. Oh, ya. Ya
Habla
tendría que
bien. Sí, pues ahí solamente la fuerza concentrada es la que está en la parte delantera, nada más, porque ahí está como de ahí usted tiene la carga, tiene cargas distribuidas del casco, carga, maquinaria. La única fuerza concentrada es la de la proa. Y tiene que colocar la fuerza de bullantez. Y está bien que usted haya hecho primero un equilibrio y sacar el peso total, ya. Y con el peso total puedes sacar la fuerza de boyante. Y es fácil porque no tiene trimado.
Es la misma, o sea, la fuerza de boyante es igual a todo el peso de la embarcación, bueno, de la barcaza, con todo.
Claro.
Sí, porque en este caso es el CB es igual a 1.
Claro, es lo mismo que el peso, ya, pero dividido para...
Dividido para 60. Sí, se acaba
para
de corregir
60.
eso. Ujú.
Y así, y luego avanza. ¿Sí? Sí, sí, efectivamente. Ya, corrijan eso y avanza. Voy a continuar con el otro grupo.
O sea, mi duda es aquí en el módulo seccional. O sea, tengo que considerar
Es módulo seccional, es sigma es igual a momento sobre módulo seccional. Seccional. No te está pidiendo inercia. Verás.
Ya.
Sigma es igual a momento sobre el módulo sección. Esto es módulo seccional, ¿verdad?
Ujú.
Ya. Y de ahí, si tú, el módulo seccional es la inercia por el Y. Pero no es esta de acá, es la de acá. Entonces solamente necesitas el S, sería M dividido para sigma, así. Momento dividido para sigma.
Claro, para sacar el sigma tengo que sacar el momento por el Y y la
No
inercia.
necesitas Y ni inercia. ¿Sí me entiendes?
Sí, sí.
A ver, deja ver. No, a ver, espérate. Espérate. Dice, estime el valor requerido del... Bueno, el módulo seccional de la casco. El min section. Sí, no. Solamente tienes el momento.
Claro.
Pero lo podemos, si es algo estimado, yo puedo tomar el valor de 235 del esfuerzo. No, porque no quiero que sobrepase el 235.
Ah, ya. Claro, o sea, lo
Entonces,
estimo con eso.
o un factor de seguridad. Incluso no 235, sino le aplica un factor de seguridad de 1.5 o algo por el estilo.
Claro, porque si no tendría que utilizar el Y que sería 5 y la inercia de la caja, considerando que es un cajón.
Claro, no, yo haría esto acá. Momento, no, porque no tienes puntal, creo que no te da el puntal.
No, tampoco.
Entonces, ya pues, no. Entonces, simplemente así, el momento lo tienes y el sigma que no sobrepase el 235. O sea, pones 235, el momento y ya está en modo seccional. Ya. Listo,
Ok.
sigo.
Dale.
1000 dividido para 44, dividido para L, dividido, Yani.
Sí, ya, a ver, aquí le pongo la rayita. Ahí se entiende.
Entonces eso sería...
Hice la del ancla.
¿Y qué es esa vaina?
Es el diagrama.
El diagrama de cuerpo libre, pues.
Ya.
Dividido para 44.
Sí, el empuje.
Ya, esto sería 150.
Bueno, la única la fuerza concentrada es esto, ¿no? La única.
¿Cómo?
La única fuerza concentrada es esto, ¿no?
Ajá.
De ahí todo es distribuido.
Esto representa las cargas distribuidas, sí.
Ajá. Bueno, avancen entonces. ¿Y cuáles serían las condiciones de frontera?
Extremos libres.
Extremos libres. ¿Y cuáles son los extremos libres?
Son
El cortante es 0
Ya.
y el momento es 0.
Dice, ya.
No me juzgue, ingeniero, que solo me confundí. No me juzgue ni se enoje.
A ver, ya. Avanzo con otro grupo. Entonces, sigan, que van bien.
Bueno, ahí.
¿Cómo van? ¿Cómo van con la distribución del primer ejercicio? ¿Alguien? Benavides, Raiza, Llanos. Benavides.
Sí, perdón, estoy aquí haciendo unos cálculos, dame un ratito, perdón, dame un ratito.
Ya, Raiza. Al menos la distribución de fuerza o el P de X. Raiza, ¿ha avanzado algo? No está.
Sí, pero sí estoy. Lo que pasa es que no me abrió el micrófono. Sí avancé la primera parte. Espérame un ratito.
Ya no, Sandy.
Sí, ingeniero, estoy haciendo la distribución de...
¿Alguien podía proyectar
Hola.
algo de lo que han hecho mientras tanto? ¿No? Bueno, ya creo que faltan 2 minutos. Avancen lo que puedan. Lo que debían es primero calcular el P de X, ¿no? Todos son fuerzas distribuidas, a excepción de la fuerza de la proa, que es concentrada. Deben incluir la fuerza de boyantez y para eso tienen que sumar todos los pesos y luego dividirlo para la eslora para que tengan fuerza por unidad de longitud, ¿no? La fuerza, el P de X es force by length, ¿ok? Entonces, a partir de allí, pues, ir resolviendo, ¿no? Las boundary conditions son libres y las condiciones libres sería fuerza cortante 0 y momento 0. Entonces, a partir de allí pueden calcular el momento y con el momento pueden, porque el sigma es igual al momento sobre el módulo seccional, ¿no? Si es a 0, podemos tomar el valor de 235 del acero, por eso yielding, y si calculamos el momento máximo, ¿sí? Podemos obtener el módulo más o menos requerido.
Una consulta, ¿tú tienes los valores de pronto del momento máximo
No
y
lo
el
resuelve.
No.
No lo resuelve. Pero esa es la idea, ¿no? Si seguiste lo que estaba diciendo ahorita, pues vas a desembocar bien, ¿no?
Sí.
Bien, ya vamos a regresar a la sesión principal. Que ya
Una
faltan
cosita,
5
perdón,
minutos.
para determinar el valor, por ejemplo, en superestructura y maquinaria, eso también tenemos, o sea, tiene un valor de ley, ¿no?
¿De
Tenemos que
qué?
aplicar momentos. En la parte que dice, en popa, dice superestructura y maquinaria.
Ahí dice, pues, que el cargo es 1000 toneladas y más winch. No,
Pero
es
150 la punta y dice superestructura y maquinaria. Dice. Hay una superestructura y
hasta su
maquinaria.
estructura y maquinaria. Dice 80, cargo 100. Pero dice que es no trims. Entonces con eso lo pueden obtener. Es no trims.
Ya que están, ya listo.
Si no tiene trimado y está ubicado
Dice que
a
todo está.
3, haga un equilibrio de fuerza, pues, un momento.
Sí, un momento, sí.
Porque dice que no trim, significa que no hay trimado. Debería estar en equilibrio.
Ya.
Ya.
Sí, ya, gracias.
Is there any questions in any group 1 through 4? Any concerns about that? Groups 1 through 4, 1 through 3. Oh no, 1 through 4, 1 through 4. Any questions, specific question, group 1 through 4, 1 through 4? Clear?
Yes, doctor. I
Yeah.
have a question.
Go on.
Carranza, group 1.
Okay.
The session modulo consider if the normal stress is 255, the value or the safe factory. No.
I don't know. The what? The what? I'm sorry.
The session modulo in the middle case.
Okay. Yeah. I don't remember the value. Can you see my screen?
Yes.
Okay. No, I don't remember the solution. I don't remember. Yeah. But yeah, you have to calculate. How did you do this calculation?
I consider the both bars and rectangular if the section modulo equal minus bending moment divide normal stress.
Yeah.
My question is,
how did you calculate the bending moment?
the bending moment is the.
What forces do you have on this beam?
Okay. Okay. I consider the concentration in the first part, the buoyancy.
Okay. How did you calculate the buoyancy?
2010 tons. I consider the CV equal 1.
Yeah, but it is a concentrated force.
Yes.
No.
No, divide length. Divide length.
It's a distribution. I mean, the buoyancy is distributed, continuously distributed.
Yes.
So you have force upward, you have force downward, and on the forward end, you have a concentrated force 150. Yes. So you have to integrate from the aft end until the midship, yes, and all of that. Okay. And what are the boundary conditions at the left end?
Free end.
So
free end in the
tell me, what are the boundary conditions of the free end case?
Shear force equals 0 y bending moment equals 0.
Okay, anybody from group who solved problem 2? Any questions? Any question from problem 2?
Doctor.
Yeah, go on. Anybody? Group 2, problem 2? Any question from about solution of problem 2? It's clear. Good. Okay, let's go to problem 3. Oh, Carranza, you have a question?
Yes, doctor. I resolved the problem 2. I confused in the result.
Why is that?
For example, in this part, for the result is equal case. Consider deflation in DI, distance I, or DL.
But the thing is this, the spring is at distance A.
A.
Yeah, and the spring is the device which is generating this force. So
yes,
you have to consider the displacement at A.
In the free end, I consider the deflation L.
Yeah, but that's not a condition.
Oh, okay. Okay.
That's not a. What are the boundary conditions at L, Mr. Guaman, in this case? Mr. Guaman, oh, you got problem with the connection. Mr. Nieto, what are the boundary conditions at in problem 2 at the right end. What are the boundary conditions? Can you see this, the problem, Mr. Nieto?
Yes, doctor.
Okay, come on. Can you see? Okay, tell me. Don't doubt. You shouldn't doubt. No? Okay, Ms. Valdez, what are the boundary conditions to the right end of this case?
Bending moment.
Problem 2.
Shear force is 0.
And the other?
Bending moment is 0.
Yeah, it's free end. But there should be no doubt. No doubt. Remember, I always remember Arquitecto Sixto Durán Bañán, when we had the troll with Peru, he said, ni un paso atrás. When it's talking about boundary conditions, there should be no doubt. Smiling. People, I'm not smiling. Okay, yes. And that, is there any other questions about problem 2? Any other questions about problem 2? Easy, right? The value of the deflection in point A should be positive or negative?
Negative.
Negative. The deflection at point at L should be larger or smaller than at point A?
Larger.
Those are ways to check your results. The shear force about this point, okay? And I have now, let's, no. I cannot. Can you still see my screen, people?
Yes, sir.
Okay. Okay, let's go to problem 3 because I have, oh man, I'm running out of time. Any questions on problem 3, people? Any questions on problem 3? Problem 3, questions? Questions on problem 3? No questions. Well understood. People, questions on problem 3?
The shear action is the force or is shear stress?
The force F generates shear stresses. The shear force, the force F generates shear stresses. The problem is that the two sticks are like this, right? If you have glue, the two work together. If you have just a little bit of glue, they will slide one over the other. So it's like having 1 and 2 beams. But if you glue them together, the height will be twice, and the inertia will be that 2 raised to the 3rd power. So the inertia of having the two glued together is higher than having the two added because they can slide over each other. This case, the inertia is lower than this case when the two are glued together. That's why you need to be sure that you put enough glue in order to avoid the shear breaking up the glue. That's the reason. Okay, one suggestion, people. Please, I need you to turn on your cameras. You see, I have, you see my gray mustache? That's experience. I'm 65 years old. The first rule for an exam is to be well rested. If you stay tomorrow up to 2 a.m. studying, on Thursday, you will be tired. You will be tired. So try to study today, tomorrow, but tomorrow, Wednesday, try not to stay awake until too late, because otherwise you're not going to have enough rest. Believe it or not, a test, a quiz, is something that demands a lot of energy, lots of energy. So try to be rested. Try to have a good breakfast. Okay? 2, when you come to the exam, the first thing that you have to do is read the question. Ms. Flores, what's the first thing that you have to do after receiving the exam? Ms. Flores.
Read the question.
Yes, read the question. I'm sorry to insist on this. What's the first thing that you have to do when you get the exam, Mr. Sawai? What's the first thing that you have to do? Mr. Sawai.
Read.
Read the question. I'm 65 years old, people, believe me. 65. I'm a grandfather. 65. I have enough experience. Read. Read. You don't understand the question? Don't start writing. Read it again. Don't understand it? Read it again. Until finally you understand what the problem is about. It is quite often, it's not only you, it's me too. I read something, I just read a bit of these 2 words here, the second line, and that's all. The rest, I assume that's wrong. You should read the whole question. If you do not understand what they are asking you, you have to go back and read it again. Don't start writing unless you understand what the question is about. That's all what I can say. Well rested, read the question. Then you can think and finally write. That's the order. Read, then think, then write. Read, think, write. Okay, people, if there are no more questions, then I'll see you
Doctor,
Thursday. Yeah, go on.
I want to say something about the evidence of
Okay.
the students. Don't forget that you have to send me the evidence by email. I have just only 10 students.
Yeah, remember,
Don't forget.
please, I was very clear at the beginning of the semester. In this class, I am the instructor. In this class, every homework is obligatory. I don't give you the choice. If I don't want to, I don't turn it in. No, you have to do it if you want to pass this class. The very first day of class, I explain it to you. I'm smiling. Yeah, I'm not mad yet. Okay, that was very clear. If you don't have the time for this class, come back next year. I was very clear. This is a very interesting matter, but demands a lot of time. Okay, so as Andy said, you need to give us evidence that you have completed the assignment. If you do not complete the assignment, you're not following our rules. That's all. Okay, is there anything else, people? I will try to, today we have a presentation here. We're going to have today somebody from Lloyd's Register. He's a naval engineer, graduated from SPO. He's going to explain what he does and more or less the idea of where his industry is going. So that's going to be very interesting. But I will be available. So if you need to ask me something, send me an email. I'll try to be open to check my email, okay? Or if you want, you can ask Isaac or Andy or Maria Daniela, okay? That's our job. Okay, people, if there's nothing else, then I'll see you tomorrow, some groups, or Thursday or Friday. Bye-bye now.